Why statistic is important in our life? Statistic is important because today we live in an information world, and much of this information are determined mathematically by statistical procedure. In all fields of science, we need to be able to utilize statistical method to conduct research, analyze data, interpret results, and report our findings. Everybody watch weather forecasting. Statistics are the key of how traders and businessmen invest and make money. Before any drugs prescribed, scientists must show statistically valid rate of effectiveness. News reports make a prediction of winner or election based on political campaign. Companies use statistics to test quality of the product. In your professional life, you will find a lot of reasons to understand why statistics is important. In all fields of science, scientific or professional, deal with population. Population could be people, could be items, could be object, could be transaction, could be reaction, preference, whatever thing, items, vehicle, laptop. I am going to represent member of the population by points. Then I can study a lot of characteristics from the population, but in statistic 1, introduction to statistics, we are going to focus our attention in only one characteristic. That my classical example, I use height of people to introduce all topics in this course. Then I want to know what is the height of men in the United States, or to test one hypothesis about the height of men in the United States. To do that, I am going to measure all men in the United States, because actually it will be very cumbersome, very expensive, and inefficient. I can spend a lot of time doing this study. It's not necessary to do that. Then statistics is very helpful because I need to select a representative sample. There are several techniques to select a representative sample. All of them use random selection. It's the basic. It's the best way because there are variability inside this population. Then my selection should be random. There are techniques to select a representative sample. A representative sample is a sample that I am going to use to draw conclusion about the population, about any characteristic of the population. Mu represents the mean of the population. How can we obtain this mean? If I study the height, I need to measure the height of all members of the population, sum all of them, that is the symbol in Mathematica to indicate sum, all of this value, and divided by my population size. That is a parameter because it's related to the population. And when I measure this characteristic in the population, the name of this data will be census. Then I can summarize this census using two parameters. One parameter is the mean, but how can we obtain the mean? Adding all height and divided by the total, yeah? But we need another parameter to describe better that characteristic, the standard deviation. Do you remember what is the standard deviation? Is the sum of all deviation, each value minus the mean squared divided by my population size. The standard deviation is one parameter or one statistic that measures how far away are all of this value from the mean. Then I have these two parameters, the mean and the standard deviation. The mean is a measure of central tendency, and it is the best representative of all measurement. And the standard deviation measures the deviation of all value respect to the center. In our example, we can use these two parameters to describe the height of all men of the United States. But it is cumbersome to obtain the census, to obtain the height of all individuals. For that reason, we use a sample. That is the objective of a statistic. Then in a statistic, we are going to use sample to make inference about the population. I am going to make inference about this mean and about this standard deviation of the population. This is sigma, a Greek letter. Then in my sample, I am going to estimate these two parameters using the mean of my sample, but I will use a different letter because this is a statistic. And for the standard deviation, I am going to use the letter S because it's a statistic. Then I will use these two statistics to make inference about these two parameters. I will use this statistic to make inference about the mean, and the second statistic to make inference about the standard deviation. Statistics is the science of data. This involves collecting, classifying, summarizing, organizing, analyzing, presenting, and interpreting numerical information. How can we organize this data? We can organize this data using frequency table. What is a frequency table? We'll organize this data according to classes or categories. Then we have classes. And when we define classes or category, then we count how many observation points fall into each class. That is a frequency table. We have different kind of data. Basically, we have quantitative and qualitative. And quantitative data could be classified in discrete and continuous. Then this is basically the classification for data. Quantitative, when we can measure one characteristic using a scale, using numbers. And qualitative data, when we study one characteristic in which we cannot assign number. We only classify, for example, color. We cannot measure. When we collect our data, we cannot assign number. But when we study height, this data is quantitative because we select one person in the population, one man, we measure the height and we assign to this man one number. Then my data consists in quantitative data. But quantitative data could be classified also in discrete and continuous. Suppose that this is the minimum value in my data and this is the maximum value in my data. So my variable or the characteristic that I am measuring can take any number between the minimum and the maximum continuously, no gaps, no batch, continuously all numbers between the minimum and the maximum, then my data is continuous. It's a quantitative continuous. But if my minimum value is this and my maximum value is this, then if my data can take some values, not all of them, a finite number of values or countable values, then my data is discrete. In this course, we are going to deal with quantitative data. We are going to mention some qualitative data in chapter 1, chapter 2, when we have a data that are qualitative, political affiliation, preference, yes or not, or undecided, we have labels or names for qualitative. But for quantitative, we have numbers. When we have numbers, it's very easy to obtain classes. The range of all possible values, we're going to divide this range in equal classes. For example, it's very easy graphically to do that. If this is the minimum and this is the maximum, if I want, for example, A classes, it's very easy graphically. I have 2 here, 4, and in total we have A class. Then, when I define all my classes, I will go to my data and I will count how many observations fall into each class. Bar chart, when we are dealing with qualitative data, is a bar chart, or histogram when we are dealing with quantitative data. All classes must have the same width. What we have done until now, we collect information from my sample, I organize my data in a frequency table, then I analyze my data using bar graph, pie chart, stand and leaf plot. I can use all of this to analyze my data. And after that, I can draw conclusion about this parameter using a statistic. This is basically what we are going to do in this course. When we deal with quantitative data, we can summarize all of these numbers using obtaining the mean and the standard deviation. The mean and the standard deviation will summarize all of these numbers because this mean represents all of these numbers and the standard deviation will tell me what is the average of all deviation respect to the mean. And we are going to study this formula later. All of this topic is a summary of chapter 1 and chapter 2. Then we are going to study probability. The definition of statistics is the science of data, and we collect data, organize data, classify data, analyze data, and also draw a conclusion about the population using my data. Despite data could be used for population and sample, let's use this only for sample in this course. If we have the information from the entire population, we are going to name directly census. But when we mention data, it's because we obtain this value from a sample. Then we can make inference about the parameter using my sample data. Also, we need to state the reliability of this estimation. And for that reason, we need to study probability. Do you know what is a probability? The chance that something occurs. But when we extend this procedure, this frequency table to the entire population, it's possible that the graph of this will be something like this. Let me show you. It's a theoretical curve. Do you know what is the name of this curve?
Bell curve.
Let's review a little bit. In this population, we have to study one characteristic. Then, if we measure these characteristics in all members of the population, we got a census. This data receives the name of census. But if we select a sample, and if we measure the same characteristic in the sample, we obtain a sample data. We can organize our data in a frequency table. We divide the range of my values in classes, and we count how many observations fall into each class. The graphic version of a frequency table is a histogram. The width of all of these classes will be the same. In this histogram, each bar represents one class, and the height of each bar represents the frequency. For example, in this class have the lowest frequency, and this class have the highest frequency. You can interpret this in this other way. You have the minimum value and the maximum value. You divide your range in class with the same width. Then you need to put into each class all observation. Then according to the number of observations that fall into each class, you will obtain a higher bar. If we extend this procedure to the entire population, and we obtain our census, and we plot all of these measurements in this number line, and we can obtain something like this, where each point represents one of these members of the population, and in this number line we plot each of these values according to each measurement. For example, this value have this measurement, this other value have the same measurement, and so on. This value is bigger and this value is bigger. When we plot all members of the population in this number line, when we organize all of them according to each measurement, we obtain this shape, and that is the shape most common in a statistic. It's a pile that looks like a mound shape, and we have all members of the population here. The center in all of them will be the mean, that is the average of all measurements. Then the histogram gives us a good idea how the data is distributed, and we can extend the same concept to this theoretical curve that represents the distribution of this variable. It is very important that you understand that all members of the population represented by one point could be organized in this number line according each measurement, and we obtain several shapes. The most common will be this, but this shape also could be skewed to the right like this, or skewed to the left like this, or could have a different distribution like this, but the most common distribution is this one that received the name of normal distribution. Normal distribution is the most important distribution in a statistic. The example that we use to introduce statistic 1 is the height of men in the United States older than 18 years old. The mean, the average of the height of men in the United States is approximately 5 feet 10 inches, 5'10". If each man in the United States older than 18 is represented at one point in this population, we can organize all of these men in this graphic. Each point represents one man. We can organize all of these men. For example, in the center of this distribution we have the mean, which will be 5'10". Then here we are going to stock or organize all men, all points that represent men that have exactly this height. Then we can use probability to determine, for example, if in this number line 5'10" is located here we have, for example, 6 feet, we can count all points located or organized from this point and up, and we can compute the probability that one man in the United States have a height bigger than 6 feet. We are going to do this measuring area instead counting point. Then until now we have covered probability, we have covered continuous probability distribution. The most important probability distribution when the variable is continuous is the normal distribution. Also, we are going to study discrete probability distribution, and after the chapter of continuous probability distribution we are going to study sampling distribution. What is a sampling distribution? Suppose that we have a population. In our example, we have all men of the United States older than 18 years old. Each member of the population represented by point could be organized in this number line according to each measurement. Remember, here are all men that have exactly 5'10". Here all men that have 6 feet. Here, all men that has 4 feet, and so on. Over this number line, we have the entire population already organized. Then we can select from this population a random sample. Random sample could be, for example, this man, his height is this other man, his height is hit, and so on. We can select a random sample. Then from each sample we are going to obtain its corresponding height. Then we can obtain a sample from this population. And we compute the mean of this sample. Remember, we have to do the same operation to obtain the mean of the population. We sum all height and divide it by the sample size. But what is a sampling distribution? That is the question. Sampling distribution means that we need to obtain all possible samples of the same size, and all possible samples of the same size. When we obtain all possible samples of the same size and we compute the mean of all of these samples, we have a new population, the population of all mean of all samples of the same size taken from that population. And then we can construct a frequency table or a census of this new population. Here we can list all possible values that the samples mean can take. In this column we have the frequency that these samples mean appear among all of these values. Then we can obtain a sampling distribution for all samples mean. We have a number line, but in this number line we are going to organize all of these possible values of the samples mean. Let's plot in a number line all possible value of the samples mean. Suppose that this sample will be represented by this point, and in this number line we have, suppose that this value is 5.8. that is the mean of all of these men, and so on. If 5.10 is repeated, we are going to plot another point. This other point represents another sample that could have the same value of this other sample, and so on. At the end, when we finish with all samples of the same size and we obtain from all of these samples of the same size the mean, we are going to obtain this pile. Remember, each point in this pile represents one sample of size n. The shape of the distribution also will be normal in our example. The center of the distribution will be exactly the mean of the population. Then we have two different distributions and two different populations. That is the distribution for individual value, where each point under this curve represents one man of the United States, and the distribution for samples mean, where each point under this curve represents one sample of size n. Could be 20, could be 50, whatever. Remember, we are going to estimate the mean of the population, the mean of all men of the United States older than 18 years old, using only one sample. And we are confident that we are going to select one sample located here in this region. Then most of the samples are organized in this pile according to its measurement. And we know that the center of this pile will be exactly the mean of the population. Then we are confident that the majority of all samples will have a measurement close to the mean of the population. Listen, all of these samples are taken from this population. Then the population will be the mother, and all of the samples of the same size will be the children. If the mother have a mean equal mu, all of the children will have a mean very similar to the mean of the mother. For that reason, most of the sample will have a mean close to the true mean of the population. For that reason, we are confident that we are going to select one sample stuck in this number line close to the true mean of the population. We can state that, for example, that 5% of all samples are located here, have a mean a little far away from the true mean, and here. Then suppose that the percentage of all of these samples represent 5% of all possible samples. Then we are 95% confident that we are going to select one sample in this region, any of these samples. Then suppose that we select this one. Then our error will be this distance. This is the maximum error that we are going to make. Then if we select this sample that is plot in this curve here, and that is exactly the sample's mean, we can estimate the mean of the population in this way. The confidence interval for the mean of the population is this value plus or minus the error, and the error will be this distance. We construct the confidence interval in this way, that this confidence interval plus the error and minus the error, the sample's mean, in this interval is located the true mean of the population. The formula for the maximum error is given by this formula Z alpha half, standard deviation of the population divided by n. But if we don't know the standard deviation of the population, we have to use this other formula. T alpha half is another distribution T score, the standard deviation of my sample divided by square root of n. We can measure this error. And at the end of the study, when we select this sample and compute this mean, we can state we are 95% confident that the true mean of the population is inside this interval. This interval actually is the mean minus the error and the mean plus the error. After this chapter, when we make inference about a parameter of the population using a sample, then we are going to study test of hypothesis. We are going to test a hypothesis about a parameter like the mean when we have a reference value normally obtained from previous studies. Suppose in our example that we have reference value for the mean of all men that is 510. According to previous study, the mean is 510. Then this is always the null hypothesis. And the alternative hypothesis is the contrary. The mean is different to this value. And we can state this alternative in this other two ways, bigger or could be smaller. How can we test any of these hypotheses? Obvious, if this study was done 1 year, 2 years, or 5 years ago, we need to take from the population right now a new sample. And we compute the mean in this sample. And what is the expectation of all possible values, all possible samples mean taken from this model? The expectation follow this distribution. That is the distribution of all samples mean. We expect that the true mean is in the center of the distribution. Then if I got a value close to the mean, we do not reject this assumption. The mean is 5.10 because we obtained in my sample a value close to 5.10. However, if I got a value far away from the mean, 7 feet, or on this side far away from the mean, 3 feet, then we have to reject this assumption. We have to reject that the mean of the population is 5 feet only in those cases when we got a value far away from the center, like this or this. That is the true mean, 510. If I got a value far away like this, we reject the assumption that is equal. That is the way that we test hypothesis. And this is a summary of statistic 1. The first chapter corresponds to descriptive statistic, in which we are going to describe a characteristic of a population, selecting a sample, measure this characteristic in all members of the sample, then we collect our data and we organize our data in a frequency table or in a histogram, and also we are going to summarize our data using two statistics, the mean and the standard deviation. Also, we are going to cover probability. After that, we are going to study probability distribution for continuous and discrete variable. For continuous variable, the most important is normal distribution, and for discrete distribution will be binomial distribution. Then we are going to study sampling distribution. Basically, we are going to study only the distribution for two statistics, the sampling distribution for means and the sampling distribution for proportion, only these two statistics, to estimate the corresponding parameter, the mean of the population and the proportion of the population. This concept is the basic of inferential statistics. Then in the next chapter we are going to construct confidence interval of only two parameters: confidence interval for the mean and confidence interval for the proportion of the population. And in the last chapter we are going to test hypotheses about only two parameters. We are going to test hypotheses about the mean and to test hypotheses about the proportion of the population. And that is all topic that we are going to cover in this course.